I hope it's something interesting to you. You're holding laptops up and talking. Is it interesting? Or is it just like more grunt work? Never mind. Sorry. All right. It's quiet now. All right. So, questions about what we covered so far? Anything incorrect that you want to fix? I should give you that. I'm wrong a lot. I almost melted down with that comment. What's that X there? Oh, thankfully I could. No, I'm glad. I'm actually glad that you made it.
Class canceled, everyone.
Oh my goodness, I couldn't.
Canceled.
Showing my true colors, he doesn't know what he's talking about.
I wish I could tell you that I never make a notation mistake in a class, but a few people here have classes with me and they have seen the revised version of the slides. The revised version of
Yes, I know that feeling. I'm still catching them in slides that ostensibly I've taught from multiple times. I'm like,
You are certainly not the first person to have the wrong integration variable.
fair enough. Fair enough. Yeah, it's just me. Just don't make your slides while you're drunk. That's all I'll say. I mean, just kidding. Or am I? Anyway.
I think that is literally the only way to make slides.
Sometimes.
It is the worst thing.
Sometimes. Or better yet, if you are making your slides while you're drunk, make sure that you give them while you're drunk too, so that you remember the state of mind you were in. That's the only way to do it. Okay, this class is spiraling. No wonder I feel very badly about how this semester is going. I feel like this has been a very terrible class. It's a good feeling to have because it's motivating, but I hope you've gotten something out of it, despite
yes.
except for me throwing stuff and some scores. What? No. Anyway, so I'm gonna scroll through this HTML file on my iPad because I'm hoping that we can just see the results. You can play along. This is the result of the R Markdown, but here I can also, in theory, draw from it. Maybe. No, maybe not. Give me the pencil. There we go. Oh my goodness, you're kidding me, right? Yeah. Okay, never mind. Anyway, maybe not drawing on it. Oh, there it is. My finger drew on it, not the pencil. So we're using a data set that comes I'm doing this to load up a couple of reasons. Number one, if you're not yet enrolled for the diagnostic model classes, consider it. This is a classic data set, if you want to call it that. It's been overused in diagnostic models. It's the Tatsu fraction subtraction data set. Have anybody heard of this data set before? Would you like to hear a quick story?
Yes.
Quick story. This data set came from Takumi Tatsuoka, who was, I had met it as a professor at Illinois. This is a description of it by Larry DiCarlo. Basically, it's this. There's 20 items in the data set. It's an open-ended math exam. It's fractions, subtraction, and each of the items is purported to be measured by a set of sub-skills itself. There are 8 skills. These are very, very algorithmic skills. So if you hear people, after working with some math, I've had the great benefit of working with math educators who are fantastic at what they do. Georgia had the #1 math ed program in the country. Really set me straight. These are not what we think of when we try to measure what people know about doing fractions. These are very basic algorithmic skills. This is not a high depth of understanding that we're getting from these data. So we don't want to emulate this, but I'm going to use it as an example because psychometrically it causes some problems. Number one, there's 20 items, there's 8 dimensions. Wow, that's tough. But number two, let's take a look at some of these dimensions. Convert a whole number to a fraction. Separate a whole number from a fraction. Simplify before subtracting, right? It's very algorithmic. So let's take a look at item 6. 6 sevenths minus 4 sevenths give us alpha 7. Subtract numerators. Okay, not a hard problem. Item 9. 3 7/8 minus 2. Alpha 2 is separate a whole number from a fraction. You have to do that before solving, right? So this is an example of the 20 items of the 8 skills. So you want to hear some other interesting backstory to this. This first appeared, or this Q matrix came from this paper by Jimmy Delatorre and Jeff Douglas. Jeff Douglas, my advisor. Jimmy, a person who does a lot of work in diagnostic models, grad school office mate. I came to these data to use in my dissertation. Jeff said, hey, maybe Jimmy can share that data with you. Gave it to me. We ended up using it in other papers, including the LCDM. Data had some 2,000 cases. That's how it came. Come to find out, like in Carlo's paper, and later on, that someone talked to Kikumi and said, well, the 2,000 cases, what are they? Or how'd you get 2,000? I would have never had 2,000 cases. Someone, right, came to me at 2,000. Someone, in the Jimmy and Jeff paper, 2,000 cited, someone took the data. If you look at it, took that 530 some odd, copied and pasted 3 additional times.
Whoa.
All right?
No.
Seriously. So, where did that come from? I don't know, but I know the data that came to me. You can see my dissertation that had it that way, and you can see Jimmy and Jeff's paper that had 2,000 plus cases. You would imagine, statistically, that would work a lot better than 500, right? Yeah, 4 times the sample size. Estimation difficulty in a maximal likelihood world. Anyway, so that's fraction subtraction. That's the Tatsuoka data. I don't know. It's a mystery to me why or what, but I used the incorrect sample size in mine. Jimmy and Jeff used it in their paper. It's since been corrected. You can find it in the CDM package itself. They have the fraction subtraction data. That mapping that we just saw of data onto Q matrix right there. That Q matrix, by the way, is a mapping of items. So items down the column, bless you, skills, dimensions, attributes, thetas across items down the rows, skills and dimensions, thetas across the columns. So it's a 20 by 8 matrix, and the skills that are measured by the item are indicated by a 1 in that matrix, otherwise it's a 0. So, whoops, that's not what I wanted. Where was I? This one? No. As I bounce around a little bit here. No, I was here. Why is that not showing? No, that's not what I want. Oh my goodness, Templin. Where's the PDF? That one? There it is. Okay. So anyway, we're going to look at this from multiple lenses. First, we're going to talk about doing so with a unidimensional IRT model. And then we're going to go into different forms of unidimensional, and we're going to culminate with that 8-dimensional model with 20 items. Does that sound like a great idea to run 8 dimensions to 20 items? No. Here's the other thing. In my 2016, last time I taught the diagnostic model class, one of the things I had students do was to try to run a 5-dimensional model using MERT. These data. Nobody in the class, we tried FlexMERT, we tried MERT, we tried all the different packages, didn't work. So, and here's the tease for my class next year. This is a foundational data set in diagnostic models. And if you want to know why that is, and it's continually used, and people have not only used it, but estimated results with the 8 dimensions before. Take my class info. I'm just trying to make it make. We're worried about that these days. But no, anyway, it's a fun field that has a lot of problems. It's still relatively new, and you'll find lots of interesting parts. But I learned so much about the rest of the field from being in the diagnostic model world alternatively. But anyway, we're going to take 20 items. We're going to put that together. Let's take a look. We're using R to JAGs because I figured out how to keep it reproducible, and because we can use the JAGs.parallel estimation to do parallel estimation. The problem with that is it'll be running, but it won't have a progress bar on your screen, because to do parallel estimation, you can actually have a progress bar, but you have to only use one chain to write it, and they didn't, but that's okay. It still runs quicker. So, unidimensional IRT, we're going to start with slope-intercept form. And I literally started by copying and pasting my code from the CFA. Right? So, here is the function. So in this is JAG's code, but in the yeah, my pencil is not working today. Oh my goodness! Right here. All right, whatever. Forget it. In this function part, within the code itself, it's all the model. Right? Whereas before in the RJAGs that we had before, we had to enclose all this in a quote. This is in an R function to make it run. So measurement model specification. We're feeling the burn right here. All right. Does it tell me how much power is in my pencil? Is that why? Do I not have a power? Come on, what's your charge at? Yeah, I guess I haven't plugged the pencil in a while.
Try sharpening it.
They have it. And there's like a metal pencil sharpener on my side of the building on the second floor over by the ITP area, right?
It's real good for those Apple pens.
Yeah. So anyway, let me just point it out to you. This measurement model I'm doing first, this is with the model data likelihood. We're looping over people, looping over items. It's easy to do with unidimensional because the specification is the same latent trait on each of the items, right? So we have our data matrix that we're going to input into JAGs. There's people and items specified in it. We're saying that that follows the Bernoulli distribution. If you screw it up, if you don't have 0 and 1 here, JAGs will complain. It'll complain in a way that's cryptic, though. they're really low on words for descriptions of what the problem is. But Bernoulli distribution.
Sorry, 0 and 1 where?
In our data.
Oh.
If we have
okay.
a non-0, non-1 entry in our data,
Sure.
it'll say something like parent, misspecified or unexpected value in parent or something like that. Anyway, this Bernoulli distribution is what we're using now. Inside it wants a probability. I've just compressed that probability into one line. We're putting the phi function, which is our inverse normal Ogive. So inside that should be a z-score. This is the parameterization I use for for CFA. Mu for the item is an item intercept. Lambda for the item is an item or factor loading. Theta, I had X factor before. I'm just calling it theta. That's the only difference. Everything else is the same. So now I have to go for each of these parameters and specify the priors. So here for theta, theta itself is down here. I'm saying theta for the person is normal, mean of 0, and then a precision of theta precision, over 1 over variance. Ignore this code just yet. That's a standardization that we can do later on to flip from estimating it with a marker item.
This is a question I should have asked
Yeah.
first week of class. When you're doing this function, does it matter in which order you specify prior distributions?
I feel like it doesn't. But there are times where I get errors and I'm like, yeah, I moved there, but no, it shouldn't.
Okay.
It shouldn't. I think they read it all, it specifies the graph of what parents and nodes are, and then they go from there.
Sure.
It does matter how many times one parent shows up, and there's sort of, it doesn't like when I do certain statements, and I still haven't figured out why. Like trying to standardize the B parameter to come up with discrimination difficulty over here was like it kept blowing up on my B, so I ended up doing that after the chain.
And can we, in theory, even specify? Doesn't make sense, but you specify the prior before you specify the likelihood?
Yeah, you do. Yeah. I put the likelihood first because I just wanted to note what things I need priors for.
Yeah, for sure.
But I think in my own, in your own, whatever your system is, totally should work. I actually think most of the students I've advised have done that first, priors first and the likelihood last. Anyway, theta is right here. We need now, it has a hyperparameter of theta precision that we're going to read in from before. Actually, check that. Now we're going to estimate theta precision because we have a marker on it. Okay? Theta precision is going to be estimated with this prior right here. It's a gamma distribution, right? It's 1 over the variance, so it's gamma with an alpha and beta. These are the hyperparameters that get read in. I'll show you, I specified this as a 1. I had a hard time figuring, before we thought this first term should be like our expected sum of squares. no idea what that should be for this case. So I just put a 1 there, and I put a degrees of freedom like 2. It's basically I have very little information about the variance of what theta should be. I'm going to save the theta variance. I'm going to take 1 over precision and save that, because that's the way I think of the world. After that, we need a prior for mu. We're saying that's normal. We're going to input a mean and a precision for the hyperparameters for it. We also need a, oh, here, I can just highlight it here. Maybe I'll do that. For lambda, we're going to take the first lambda and set it equal to 1 right here. And then below that, the rest of them, I'm actually going to allow to be normal in this case, right? So this is the case where, because I have a marker item, I don't need to worry about putting a log normal on the lambdas, which is actually good because this will, these are conjugate priors for the method I talked about for data augmentation. So this will enable an algorithm that will go much more efficiently than other versions. Questions? Okay. So now here comes the fun part. For the item intercepts, the hyperparameters, I set the mean of the prior distribution to 0, and I set the variance to 100 right here. I used to have that as 1 million. But remember, the scale is different. I thought, I'll try 100. And it didn't seem to have much of an impact because, again, we're talking about the range of y on this case is truncated by it being a probit value, right? The precision is 1 over the variance. Same thing with the factor loadings. I gave it the same prior. Again, for the theta, I told you this just a second ago. The variance, the original variance, I set to 1. The expected sums of squares I set to 1. Actually, I set the degrees of freedom to 1. So now I have to create the data that JAGS is depending on. I had an n, I had x, I had I. These are all the looping variables. X was the data set. And then each of the hyperparameters I put in. And then I need to specify what I'm saving. I'm going to come back. You'll notice there's a theta s right here. I'm going to specify that or talk about that shortly. We'll come back to that in just a moment. Now, I set my model seed here. And because now in the JAGS, the R to JAGS package, I could run JAGS.parallel. And JAGS.parallel takes input, the same input that you have here, that you would run with the JAGS function from R to JAGS, which you've run before, you've seen me run before. There's 2 differences. Number 1, you have to specify the model seed for parallel items to have reproducible results. That was the catch I didn't see before. Number 2, if you try to give this as variables, in the way that R calls its cluster, you have to pass the environment to each cluster, and they didn't do that. So it goes in that environment and looks for a variable name and doesn't know where the parent environment is. It creates a cluster of its own parent. So it passes the literal numbers, but I couldn't get it to pass saved variables to it, and so I gave up after 5. So here you can see I'm running a 2,000 length iteration total with 1,000 burn-in over 4 clusters, and I'm saving every value. There.
Either I missed it or I'm confusing RDJAGS and JAGS, but we didn't specify initial values.
We don't have to in this case. JAGS will create them for us.
Sure, we never have to, right?
No,
They always
in the
use-
RJAGs we actually did because that was the way we could get reproducible results.
Okay, I got you.
In that clunky, there's this long line of syntax. We have to have a list, and we have to specify a sampler and a random number seed for each. Here, actually that code that I found to do, I found because I looked in the RTJAG syntax and what they were doing for it. Here, when I took the 10,000 foot view of it, passing this seed, it does all that code and sets the seed right for each of the clusters.
Sure.
The cluster, by the way, is a parallel process in R. Yeah.
The number of clusters have any relationship to the number of chains? Can you have a bigger number of clusters and number of chains? Or?
It will. I do not believe it matters. I think what they've set it up to do is 1 chain per cluster.
Okay.
So the chains run in parallel. I may be wrong about that. That might be something that you can see in the results. But I believe what was happening, it was saying is, if you didn't, you don't have to specify the number of clusters. It will try to figure that out based on the number of processors on your machine, number of chains. But I'm actively saying this to try to make one chain run per parallel. How many processors do you have on machines? How do you even tell? For those of you in Windows, it would be under, well, here in Mac, activity monitor is what we use for it. And here you can see the CPU, the disk itself. Oh, no, that's not it. Well, maybe not. Anyway, I've lost it. Down here, the CPU load, well, you'd see multiple streams with it, and I've lost where it is. In Windows, you have a similar thing. I can't remember. It's in the, when you look at the processes running, you'll have a graph, like of each of the processes. The number of graphs you have is the number of cores you have in your machine. And that would be a cluster here. So a lot of the processors will have 4 actual cores, and then with each core, it's actually 2 virtual cores. They're hyper-threaded is what they call it. So it'll be like 8 for many of your machines. Hope that helps. Okay, let me see if there's any questions. They must die. Death to thresholds. Okay, so it ran. Music was playing, it was awesome. Here's the output. These are all the parameters of the model. We have our average, we have our posterior mean, that's a mu vect. We have our posterior standard deviation. We have our quantiles of the posterior distribution. But the question we must ask is, sorry for all this output, that's one of the problems with this. Keep going. What is the convergence? And that's where we need to come back to, whoops, that's theta s. Here. The last 2 columns are r hat and the number of effective sample sizes, right? So here, let me take my mouse off. Oops. Okay. So here, r hat tells us convergence. We want that to be less than 1.1, and you'll note for almost every parameter we look at, it worked. Bless you. So even for the thetas, it looks pretty well converged.
What would you do if you have a complex model and there's like one parameter that did not converge, and it did not converge in a very bad way?
Probably just cry.
Yeah. I mean, would you be like, my model's mostly good, let's make some inferences?
Yeah, that's pretty much what happens.
Yeah.
I think what you end up seeing, what I like to do, I didn't do it in my syntax here, I like to break down convergence, like what's the maximum r hat by type of parameter. Because in a lot of these models, particularly in, when you get into mixture models, it would really be bad. Theta itself could be a problem. There's a lot more theta. So I want to talk about maximum and then proportion less than 1.1 or proportion less than 1.2.
I guess if you had all the time, you really always just tighten your priors,
That's
or
typically what's done.
increase your number of iterations by a lot, because in theory they will converge eventually.
There's another problem with it though. If you have a really complex model, you can fake, well, pardon me, Bayesian identification is such that if you have a model that absolutely shouldn't be identified, you can make it identified by tightening priors.
Yeah.
So I think the first thing to check whenever you have a really tricky convergence issue is my model identified, like from a non-Bayesian sense? If I were to put uniform priors on everything, do I have model identification? And a lot of times that rules out, that's the problem. There's some weird lack, there's usually pairs of parameters or groups of parameters that don't converge, and that's kind of giving you a clue to where the identification issue is, because they'll flip or they'll go in sequence in ways like the autocorrelation or the posterior correlation from is like 1. So I think I'd go there first, but then after that, tighten the prior.
I guess in a really extreme sense, if you really have an issue, you could fix the prior.
Yes, you could, or you could fix the parameter, right?
Yeah.
Mm-hmm. Yep. The most extreme tightened prior is one with a degenerate distribution, which, by the way, is the best stat term ever. That distribution with no variance is degenerate. When I think of degenerates, well, think about making slides when I'm. So So things converge. I summarize. Here's the summary that comes from it as well. These are all the item parameters themselves. I broke it down by parameter if you wanted to not scroll, but there's mu, there's lambda. So now the question is, did it fit the data? So what do we both bring back? Our friend, the posterior predictive model check. However, it's a little bit different now. Unlike in CFA, we did posterior predictive. If you remember CFA, we did posterior predictive model check for correlation, for like standardized root mean squared residual of the correlation matrix, and for the RMSEA. We don't have RMSEA in a default case for IRT. We don't have standardized root mean squared residual as easily. I guess we could come up with that. And correlation is a problem as well, because there's two kind of bad options to do correlation in binary data. Like, there's actually lots, but let's go with the two that were the most analogous correlation to continuous data would be a tetrachoric correlation. The tetrachoric correlation is not guaranteed to be identified for samples that you get. And plus, it takes longer to calculate. The Pearson correlation doesn't necessarily range between -1 and 1. It depends on the marginal frequencies, and only does so when they're 0.5, I believe. So now you've got a truncation of correlation that could be odd as well. So I'm going to ignore both of those. The book talks about a conditional model fit measure, conditional on theta. I'm not comfortable with that. That doesn't mean I don't disagree yet, I just haven't done the research yet. And the research I know from other paradigms is any model fit that's conditional on model parameters is suspect. It'll start to look different. We want to get an aggregate model fit onto data without conditioning on parameters. That tends to be the best model fit situation we're in. So I'm going to look at the covariance matrix of the data. Now there may be problems with that as well. That does show up in the model fit literature. Some of Sandip Sinare and papers, Johnson talks about it.
It seems like with the conditional model fit, like you condition on theta, right? So for an item in a data set, for a theta.
Right, yes.
The that works, go across all thetas, all items, all data sets. Like, you could do that.
Yeah, well, that's what we're sort of doing. What I'm doing here is sort of saying I'm already generating, I know the distribution of, part of my model is the distribution of theta. So let's just not anchor our thetas to these people. Let's go across the distribution. There's sort of ways that we could have taken each person's theta value and generate data on it. That's conditional on the value of the current chain. I'm saying, forget it. Let's ignore the people part of it. Let's just try to integrate across all possible people and just take a sample beyond theta. But anyway, there's lots to be that I don't know about, and I think there's lots that the field still hasn't considered with it as well. So to do this, let me just go through what I did. You create a posterior distribution. The R to JAGS has all the data in one matrix. So that's where we remember the first time we had to take all the chains and lump them together. That it's already in a matrix, so I just renamed it to fit with my syntax from before. I figure out which columns are mu, which columns are lambda, which columns are theta. And all I'm saving here is the simulated covariance matrix from each step in the chain. The same process follows. I grab a random iteration. I figured out mu, lambda, and variance of theta. I grab those from my posterior chain. I generate a set of thetas for people this time. So in the CFA world, I just generated data based on a sample. I took the model parameters, created the model implied covariance matrix, used that in multivariate normal, and created data. We don't have that as easily here in CFA and IRT data, so I create theta first. So I create a sample of people's thetas from a normal distribution with the variance equal to what I'm estimating in the chain for theta to be. Right, so now I have a brand new sample of thetas, ostensibly from a population of people that looks like the model thinks our population is from. The sample size is equal to our sample size of people as well. From those thetas, I make probit values. Now this is where the matrix math gets kind of fun. this here, here's my mu, right? So everybody, for each item, there's a mu. So if I take mu, the vector of mu's, transpose it, right? So vector of mu's is 20 by 1. I need a 20 by 20 block, right? So I multiply a vector of 1's, 1 by n, or sorry, n by 1 times 1 by 20, and I get a n by 20 block of the means, where the mean for each column, it's just that mean, that item intercept. So that's the anchor. And then I take theta times the matrix product lambda. Theta is a matrix product of n by 1. Lambda is 20 by 1, but I take the transpose. And so then I get a n by 20 product there that I add together, and that becomes our response function. So I don't have to loop. Looping takes a long time in R, so if I could fast forward into a matrix product, I'd try to make that work. So that gives me the probit. I didn't take the, now convert, so this is like our z-scores. To convert those to probabilities, I need the p-norm function right here. Right. But really what I'm going to do is generate data from binomial. I generate enough data equal to my sample size, and I have each trial, there's one trial, that's what the R binomial says, and this is the probability given by p-norm. Now this is one I had to loop over. So I create each of the columns. I couldn't just give it a block of matrix. I could give it a vector, but I couldn't do it a matrix. Not that I'm aware of, at least. There is a way you could probably do this with, what is it, v-apply or m-apply probably. I could probably do that better, but I'm not as good at that, and I need to do this in a hurry. So then once I have my data, I just save the simulated covariance matrix. Hey, look, there's my progress bar. It ran. Let's take a look at our numbers here. Here are all of, this is where I'm going to go and show histogram. This is the model, this is the model implied, or the simulated data for the covariance of item 1. Sorry, this is the variance of item 1. It's the first term in our simulated data itself. Here is our density for it. That line is what our item's true value, or ML estimate from the data was, right there. Kind of interesting, right? Look at that range, it's very narrow. This is a variance parameter. You never really think about that, but for our IRT model, the variance, if we know the mean, we know the variance, and we should be getting these variance parameters without question, right? Because the means are almost always spot on in our model for IRT. Not always, depends on our constraints, but the variance should be as well. So this is like the first term of the diagonal of the covariance matrix. I also went and then I went through all of the covariance matrix. I computed the empirical CDF for my posterior sample for each value in that covariance matrix. I didn't actually just take the upper triangle. I just kept all the values there because I'm sloppy. It's all right. And then I took each observed value from the data's covariance matrix and computed the percentile measure for it. And then I flagged the items that had percentiles that were in the upper 2.5 or lower 2.5 range. So I like to think these are the items that have issues. And so this is actually, this is the whole matrix. So you'll see item pairs there twice. So item 1 with item 2 and item 2 with item 1 have the same statistics with it. So you can think of the number of items actually half of this right here. But you'll see there's some 60 items with problems. Or sorry, 30 items with problems. 30 item pairs with problems. How many item pairs do we have, right? 20 times 19 divided by 2, what is that? 190? So 30 out of 190 had problems. Is that good? I don't know. I don't have a normative basis. I think some of these are pretty bad. Take a look at the percentile rank. Many of these have a 1 or a 0, meaning we never generated data bigger or smaller than that value. Right? So, okay. Questions? Yes?
So in the outline, like for the summary, statistics that you make, there is like naive standard error and time series standard error. Can you explain?
Well, the time series standard error is supposed to be the standard error when you factor when you take out the dependency based on the autocorrelation. Naive standard error is the one I use. If we don't want to go and sort of the projection from the time series is not sufficient for me. We want to say that we sampled the whole thing. So having the naive standard error really detrends the data and looks at the standard deviation that we really want it to be. I don't prefer the other one. The other one depends on autocorrelation. But if we sample enough of our chain, if we sample enough the posterior, it gives us pretty good estimate of what the standard deviation should be. Other questions?
So when you write a result section,
Uh-huh.
how do you present that output using the table?
I would take, for the parameters of the model, I'd put those in a table. So particularly for a unidimensional IRT model with 20 items, each has an item intercept with a standard deviation. So I put the mean and the standard deviation in the table. Sometimes I'll put like a HPD in the table, right? A 95% HPD. And so that shortens the number of things you need for. But effectively, think of it as you want to give enough information to sort of recreate the results or compare results if someone wants to recreate the analysis. And plus, also you want to talk about the mean and the standard deviation of the uncertainty. Hope that helps. Good question. Thank you. Thank you for asking. Other question. So, to summarize, IRT here, almost identical to CFA. There are two big changes. First is instead of denorm for our data, there was deburn. We felt deburn. Oh, depuns. Terrible. See, the thing is, if I was writing software, I'd have like a depun statement or something like that, and it would just, every time throughout the chain, it'd give you a pun, like for every iteration. It'd be kind of fun. It's like, I'm just doing this to entertain myself, right?
Random messages like, how's it going, bud?
There you go. So I noticed you're waiting. Let me give you some reading material or things to ponder.
We're like, you know this analysis is going to fail, right?
Oh, this is not going well. There's some and then at the end it had like dun dun dun, like it's done. This dramatic ending to, anyway, never mind. I've lost my train of thought. Deburn was one difference. The other was we don't have residual variances on the items. We don't have the unique variances because there's no term for that in the Bernoulli distribution. That's basically it. Right? Two changes. That's it. IRT is CFA with two changes for the effective. Now we can standardize our estimates. If you didn't like having theta having a variance, I'm showing this to you because you may want to have a theta with a standard deviation of 1. That is not difficult to do. Basically, we need to take theta and multiply it by 1 over its standard deviation, the square root of its variance. Similarly to that, in the slope-intercept form, when we standardize theta, we have to go then standardize the loading or the slope with it. Because really what we're trying to do is show the core, or mu plus lambda times theta, is equivalent when those are standardized. And so when we divide theta by its standard deviation, if we multiply the standard deviation times lambda, the standard deviations cancel, we get our same core. We don't have to do anything to mu in this case. It's different in the discrimination difficulty case, but it's not here. So we did that. We could also transform to discrimination difficulty. I did so with the standardized loading, or the standardized theta, because that seems to be what discrimination difficulty is all about as well. You'll see in my syntax, I put, oh my goodness, this is tough to get to. Let me just touch. That's why the touch screen is for, right? In the syntax, this is up at the top where the syntax is. Here's my theta standardized for each step of the chain. Oh my goodness, this is a mistake. It should be the square root of theta variance. Oh, standard deviation. Standard deviation. Templin. Oh my goodness. Huh. Screwed up the dx. Screwed up the theta standardization. This is what I think of standardization too. Anyway. And then you need the standard deviation to multiply lambda down here. That gives that to you. What you will also see is that, get down to where I was, oops. No, don't do it that way. That's model 3 now. What you will also see is that if you want the B parameter, I couldn't get it to work in the code because I kept making a JAGS error that I couldn't troubleshoot. And so I did it outside of the code, if I can find where I put it. Too much output, 341 pages. Gosh, I hope he didn't print this. Think of all that toner you'd use. This is model 1 still. Nope, this is model 2. I'm getting closer. All right. Here we go. So here's my loop. I just looped over. This is sort of the same code I had to build to do the posterior predictive check. I went over all the replications. I created a brand new B value, and I just created that based on the terms from the model, right? It's -1 times mu over lambda. And here I actually had, it's unstandardized, and I needed to put a square root there too. At least my syntax was right. My notation was correct. The syntax screwed up. My apologies. Questions? You want to see the same model as phrased as discrimination difficulty? All right. By the way, before we go too much further, so I saved all this in R, by the way, so that I can actually talk about it with numbers. I pity you, because if you're running this and trying to get these numbers, you're not going to be able to repeat this. But if I wanted to show model 01, here's my result. I'm doing that. Uh-oh. Hang on. Having cognitive difficulties to remember what I'm doing here with the code I want. Yeah, this is it. I want my. Nope. Why am I not seeing the DIC with it? Well, here, one thing I can show, because R2JAGS gives us the Spiegelhalter version. Okay, DIC. Oh, never mind. Yeah, DIC. Yeah, you got a DIC in there.
Thanks, R.
There. Hey, I kind of want you to see the DIC. Yeah, I got one. Good luck. Sorry.
Equivalent of, can I see the DIC? I don't know. Can you?
Exactly.
Thanks, R.
Thanks, R. Piece of shit. Okay. Yeah. You know, I do love R, but at the same time, R sucks. I said that. Oh, no. Okay, let's do this discrimination difficulty. What you're going to see is, to make this work, I used to standardize theta here. Right? The code's much nicer. It's shorter, right? Because I'm going to standardize theta, meaning I don't need hyperparameters for theta's priors. So I don't need to go and put priors there. I have A times theta minus B, and then I have A, B, and mu. A, though, I had to make log normal. B was normal. Mu, I just created the mu version of it if I wanted to go transform between the two. But you will see now, with that, we can run our analysis, and here are our numbers. This is more of a scale I'm used to seeing, so I can interpret these a little bit better. And here's our item difficulties. Remember, this is the 50-50 point of getting the item correct. The smaller the value, the easier it is. So like, here's a relatively easy item 6. The larger the value, the more theta it takes to get it right. So you can see what those are. You can see our standard deviations. I'm not even interpreting models in this class. I'm like, oh yeah, psychometrics, yeah, we have tons of classes on that. Questions? Okay. If this hurts your eyes, don't look. Scrolling a lot. I also redid the posterior predictive model checks with A's and B's. And you'll see, again.
In most cases, we don't really have a good objective sense, though, if our model is working well?
No.
We look at the correlations and, you know,
Here I'll note, though, with the A and B parameterization, there are 72 pairs of items that were bad, whereas before there were 30. Sorry, 60. 72 divided by 2 is what, 36? 36 versus 30. They're not the same posterior in this case. So the model fits differently. Which is what you wouldn't think in the frequentist world. But here, in an absolute sense, I don't think this is doing well, personally. Questions? Want to put a C parameter on it? I did that too. Oh, no, don't do that. This way. Okay, 3 parameter normal ogive model. I'll bet you can guess where it's different. Again, A, B, and C show up here. I'm just sticking with the simpler code this time. C, and the deburn, the probability is C plus 1 minus C times this BC. That's it, that's the difference. Now we need a prior for C. I have a C with a D beta, a beta prior. And I actually used, don't tell the rest of the IT world, I used a uniform. Oh, a beta is a uniform distribution when the A and B parameter are both equal to 1. And I set the hyperparameters 1. You think it worked? Let's find out. Here's our numbers. Did it converge? Well, look at those C's first of all before I come back to convergence. This is an interesting case to me because a number of these C's are down at 0, right? C4, C5 are not, C8, C9 are not. The rest of them are practically 0. I'm in 0.34 here. And take a look at the posterior standard deviation of some of these. This is a 0.44 with a fairly small posterior standard deviation. This is 0.24 with a fairly large one, right? You can imagine what the shapes of these distributions are, but I'm not even going to try to plot them right now. Stumbling enough. Let's go see convergence, though, which means I have to get all the thetas out of the way. Here we go. Look at the convergence of the C's. That's pretty darn good. The R hats are really close to 1 for all of these.
530.
These are the effective sample size. This is trying to factor in the autocorrelation with it. So it's not a big sample, but I was trying to go for something that was practical for our class if you wanted to run it. What do you think? Questions? So I would say convergence has been achieved. Would you? Okay. So let's take a look at model fit. Once again, I took the syntax I had before. By the way, there's DIC, 8567.8. And if let me just grab these right here. By DIC, here are the 3 models. This was slope intercept 2 parameter, discrimination difficulty 2 parameter, which ironically, the DIC was smaller, saying it should be preferred, yet the number of item pairs that were flagged on covariance was higher. Ding, what do you expect? Thanks, Snapchat. And then, by the way, it's my communication line to my daughter. I'm not like one of the olds, like, I'm on Snapchat. It's the only way I talk to my daughter pretty much. And then finally, this last one. This would lead you to believe, you want DIC to be smaller, so it would lead you to believe that the 2PL did better than the 3PL in this case, slightly. But there is no range for DIC, problem number 1. Problem number 2, there's better versions of ways of calculating DIC than this version that's been done. Something by Gelman, there's another one by Plummer. So I'm taking this with a grain of salt. Even though I ask you to do it in your homework, because that's sort of what's done.
Well, it would be more interpretable maybe if the differences were larger, but those are really close in value. So.
Yeah, they're basically the same models, it's telling us. Actually, if I were to make a case as to why the DIC for this low model was very close, there were only a few C parameters that were really not close to 0. And so I think what this is telling us is for those items, we probably should have made them 0. If it's not justifying the addition of 20 C parameters, maybe we could have gotten by with 2 or 3. It's probably, if I were to justify these numbers, that's what I'd say. All right, let's look at the posterior predictive model check. Here I've done it for A, B, and C. You can follow along with it if you'd like. Here is, I was doing this before, what's the count? Now, the number of pairs of items that are having problems fitting, it's like 207. It shouldn't be 207, but it's 207. I thought these were pairs. Evidently, I may have done something wrong, but it's really not doing well. Okay. 207. Why is that odd? Anyway, C parameters causing all sorts of weirdness now. Questions? Okay, here's the exciting ending of the class. Back to the multidimensional IRT model. By the way, good luck trying to get this to work in ML. You may be able to make it work in some of the Bayes analogs with ML, like like in MERT, the default is a Bayesian version. It sort of does a Bayesian E step, and then you can do M after that. Robbins-Monroe, I think they call that. Here's our 8 dimensions. There's our Q matrix. We're going to estimate an 8-dimensional MERT model with 20 items. I need to see if Lisa's still listening, because right about now is where she'll be like, no. No. This is incredibly, I believe she would call it stupid. I say that because our son, evidently that's in our vernacular when we talk about things at home, because there was a time when he was 2 and he got in trouble at school for saying, you're stupid, you're stupid. He didn't know it was bad. And then one morning he was mad and he said, well, you're stupid right now. So that's always been attached to like what we talk about now. This is stupid right now. Why is this a bad idea? Let me ask you that. Look at this structure here. Let's take a look and let's look at the number of items per dimension. Number 8 has 3 items. Minimally sufficient number of items for this in a maximum likelihood sense is 2 with the covariance. In Bayes, it's actually less than that, but they're really not good. Remember, the Bayes, there's ways of tricking identification. So for us, we're going to keep that 2 with covariance estimated as a minimally sufficient condition for us. But look at dimension 7 here. Oh, that one item. Are you sure they forgot?
Yeah.
That's not a good idea. If a dimension shows up on every item, I guess maybe it's like a bifactor. I don't know. And then dimension 6, there's 2. Dimension 5, 1, 2, 3, 4. Anyway, the point is, number 1, if you looked at this and you expected to get numbers or thetas of those dimensions that had any type of reliability to it, which we'll talk about next week a little bit, you can't expect much with only 2 or 3 items per. But now look at the other equally ridiculous thing. Take a look at like item 4. How many thetas are on item 4? 1, 2, 3, 4. 4 thetas. Wow, that must be tough. I think there's a 5 in here somewhere. Point is, this is a ridiculous amount of structure. There's no way this is a good design for an assessment. It's no way that's a good design for a psychometric version of the test. It's pretty crazy. What do you think? But I'm showing it to you not because it's a good idea, because I was at an event with Ariel last night and I said, well, I'm going to show this. And he said, oh, that's not going to work very well. And yet I got it. And I got numbers out of it. And yes, we're going to assume it didn't work very well. But even saying I got it to converge was impossible for me in other classes, because without using a Bayesian system to estimate things, like a likelihood or a frequent, or like an optimization scheme, to estimate this using marginal maximum likelihood, like an EM algorithm, or like just a straight quasi-Newton or whatever, we have to integrate across 8 dimensions of theta. That means 8 So let's take M plus. M plus has a default of 15 quadrant nodes or points per dimension. So that's 15 to the 8 points for any calculation that involves a marginal value for a person. Right, that's how. What is 15 to the 8? Let's find out. Make a point of this. That's how many calculations per person for any marginalization you would have to do an EM or otherwise, or a marginal maximal likelihood version of this. That's tough. I just see some snark. Stupid right now. Yes. That's stupid right now. So it's a bad idea. But my point in saying this is really why I'm teaching this class, is that multidimensional psychometrics are out there. They're virtually impossible to do in a stable way with algorithms that aren't at least partially Bayesian. Right? And that's where Flexmert's novel part was this Robbins-Monroe algorithm. Same with Mert. It's half Bayesian, right? It's doing Monte Carlo steps throughout. It's a problem. Not a problem, it's just, that's how it works. Or M plus is a Monte Carlo integration, where basically instead of integrating across these calculations, whatever, 200 trillions, I think it might have been in billions, hundreds of billions of calculations per person, it would take a sample of 1,000 of those per person. Because that's a good approximation to this 8-dimensional thing. Let's sample 1,000 parts of it. Right. That's a good idea. Anyway, point being, MERT models sound great in practice, but think of it, we've switched, all we did to get between CFA and now was switch to deburn, right? Maybe this is a metaphor for politics, but when you switch that way, it's a lot harder. Right. When you switch from normal to deburn, denorm to deburn. If only we had a candidate named Norm. Because that would totally make it work. Anyway.
Plus, every time that we go out to give a speech, people go, Norm!
Norm! Exactly. Denorm. Deburn. Never mind. Depuns. We've just made fairly minor switch, and it's virtually impossible to make it work. But I'm going to show you it worked, okay? And then, as to why this worked in a DCM framework, diagnostic model framework, I'll have to come to class in the fall. Just pointing it out there. Just put it out there. And if I do it right, we're not going to have to use JAGs in my class. We actually can't do JAGs to do what I have my own stuff to give you, and it won't be code like syntax like this. It will be it'll be like more like LM syntax. Be much shorter. Do much of the hard work for you. Okay? Maybe. We'll see. So, how do you write a multidimensional item response model here? Again, we're going to use deburn, but instead of looping across people, I'm going to create an item-specific syntax per person. I don't know that I can... Oh, shoot. You're kidding me, right? I know where I'm at. Okay. So here, for each item, I went through the Q matrix, and I put a lambda for each entry. So I have a lambda matrix now. It's a 20 by 8 matrix that has numbers in. And theta is now, for each person, an 8. It's an n person by 8 dimension matrix as well. And so every time you saw an item measure one of those dimensions, I've got a lambda and a theta for it. Yes, I did this for all 20 items. For the prior distributions, for theta, I'm using DM norm, multivariate normal. I had some issues with this before. I had to specify the dimensions of all of my matrices to make it work. But anyway, I have a kappa, which is our factor means, which I'm going to set to 0. And then I have my inverse covariance matrix, which is D. Wishart. And I will note I'm going to give it the D. Wishart here an 8 by 8 identity matrix as an input for a hyperprior. It's trying to put less weight on the covariances. And the other error I made was that this thing, the degrees of freedom, has to be greater than the number of variables you had. And so it might be variables plus 1. I made it 10 just to make sure it worked. The item intercepts are still the same normal distribution. And then for the lambdas, for each dimension, I put a marker item in. I had to put that marker item in because the way I'm generating that Wishart distribution for the inverse covariance matrix gives me all the terms. So I need the factor variance identified, available. So you see the ones here for the marker items. The other items in the loadings or slopes are all the same that I had in the slope intercept form before. You'll note these are d-norm. These are not dl norm. This is not the strictly positive version of it too.
Which is fine since we have the markers.
We have markers, yeah. It's not going to give us that, when the marker items, we don't get that crazy multimodality because we certainly set one of them in the direction we expect it to be. Now we may get something else. If that one had a negative loading, if we were to estimate it, then all of them might be negative, but that's probably a smaller chance of that happening. Now you'll note, to make this work, I ran it with the same 100 value for my variances for means and item intercepts and item loadings, and that didn't work. So I actually I shrunk it down to 1 to make it work. It ran. I actually had to run a little bit longer. I made a 10,000 length chain, 5,000 burn-in. I also had a thinning interval as well. So when that happened, now I've got to go through a lot of output to get to the R hat. Shoot. Here's R hat. These are R hats for thetas, but you can see this middle column right here are the R hats. They're all close to 1. I think I would like to argue, and perhaps you'll argue with me. Or perhaps I could convince you. Look at those R hats. Yeah, like this one's not great. That one's not great. I'd probably want to go and see what that, but the Muse are doing all right. There's a couple ones. I'd like to say, for the most part, it's converged. There are 1 or 2 that were a little bit big. Those are probably ones that we want to get rid of anyway. So now I can go back up and take a look at those lambdas. Son of a gun. There we go. These are the slope-intercept deals. These are the slopes. You can see the values for a lot of them. Here's one that effectively 0, another 0, right? You can imagine where some of these have 0 within there. Heck, you can just look here. A lot of them shouldn't be there. In fact, for some of those factors where we had only 2, like one of them that wasn't the marker was like 0. So it's pretty messy. So what do you think? Does this look like a model that we should consider?
Yeah.
Let's take a look at DIC, shall we? Let's take a look at relative model fit. I haven't looked at absolute model fit yet. It's bigger.
Yeah.
But this is my worry about Wishart, but that's not too bad. Let's take a look at model fit. So at the end of my code here, I created a posterior predictive model check again. Similar way. You want to know the number of items that had flagged covariances? I know you're looking at the clock. It's almost over. Here's the big ending. 4. 4. So in an absolute sense, the data I'm getting is this fits much better than a unidimensional model. Whoa, there's the cliffhanger. What? Exactly, right? Isn't that amazing? This was like 70, or 70, it's like, remember, it's half of this. It's like 72 before, or 60. 4, 8. So, sort of the interplay between model complexity and model fit, right? A more complex model should fit the data better unless the complexity is stupid. Like we added C parameters to this, for instance. That's a terrible idea, right? Or D parameters, or D without a C. It's another terrible idea. What do you think?
That kind of makes sense, though, right? The more complex your model, the more, in a vague sense, you are constraining what your data looks like when it comes out. And so you're saying, hey, it has to look like this.
Yep.
Well, guess what? It kind of looks like your data, or the correlation. fine.
And even with this, though, take a look at the culprit item. Item 8 is the one that's implicated in everything. Right?
I guess another way to think about it, people often say that if you over specify your model, you're fitting to noise more than
Also true.
truth.
You could be doing that here. Item 8, by the way, only had one loading on it. Or one item. Anyway. So, does that blow your mind a little bit? Or is that just a demonstration of what we should probably already know, which is more complex?
So, DIC have, you suggest that DIC has high penalty to model complexity?
It has a penalty for model complexity, yes. Hmm?
I think what it demonstrates is that there aren't a lot of good ways to check model fit.
Right. Exactly. And I would even go so far as saying that's true as well in the non-Bayesian case, but we've come up with an industry of people who put norms in that say, hey, it fits good if it does this. So.
Well, I think what went down like the ML or non-Bayesian way is that model fit is more intuitive. Like you can kind of figure out what's going on and how that works. And
Right.
interpret it. But posterior predictive model checks are less intuitive and more technical and harder to get through.
Yeah, I'll say. We just have like 3 minutes left. I'm going to mention homework because I got to do this. Just because I got to like give you a chance to practice. It's not because I hate you. It's because of that. This homework's a very similar structure to the last 2 homeworks. Find an article, see how people have played with Bayes, and then there's an example data from a paper from Lisa Hoffman. It's also in the CDM package. By the way, they were put there without anyone asking us.
Huh.
They were on my website. They just put it in. So this is fine. It's not my data. I had it on my website. I probably shouldn't have done that. Yes, it's a publicly available thing, but if someone's going to cite the data that they used in R, they're going to cite these people in the package, which is really funny. Interesting world. I do ask you to go kind of resample the data so you can get a different number for each person, a different result. But this is it's a 28 item test with 3 attributes, 3 skills. I ask you to do a 3-factor model, a 1-factor model. The saturated model in this is really crazy. I won't talk about it yet. I won't talk about it at all. That's basically it. Same structure as the homework before. Hopefully you could be able to adapt what I did in my syntax here. I don't tell you which way to do the model except for using a logistic model. You can do slope-intercept. Don't do a 1PL. I guess I should put that there. Heck, you can put a 1PL. I don't care. Do Rosh, fine. Be awesome. Just remember, when model doesn't fit the data, that's the data's fault. These data are screwed. All right, I'm going to stop here, but if you have questions, you can ask me after class. I thank you for coming. I will see you next week. Next week is Polydamas IRT, and we're going to talk more about theta. And the one thing I want you to think about when we go is item information. We're not using maximum likelihood. How do we calculate it? Whoa.